Yeah, distribution. The term distribution refers to collection of all information, all probabilities related to a random variable is called the distribution of x. So if you're given the distribution of a random variable, it means that you have either a probability mass function or a cumulative distribution function. From cumulative distribution function, you can also infer the probability mass function, or in the case of continuous variables, probability density function, uh, which is called the PDF. But the cumulative distribution function serves the same purpose in both the discrete and random variables, and it's defined as it's as this: the probability of the random variable to have a value of x, which to value of x or less, or the probability that x is less than or equal to this lowercase x. That this probability is also defined by this cumulative distribution function, which is indicated by a capital F. So capital Fx, when you see this capital F, it means the cumulative distribution function, cumulative probabilities all the way for all the events from minus infinity all the way until this value x, including x. Okay, so it's inclusive, therefore less than or equal to x, like this. And by the way, in the case of continuous random variables, whether we have included x or not would not matter, because at that exact same point, since the probability is zero, probability of x less than x and probability of x less than or equal to x will exactly be the same in the case of continuous random variables, because probability of x is equal to x, that event will be zero. The probability will be zero for in the continuous random variables. Okay, but for discrete random variables, there's a difference. Probability getting this equality sign makes a difference when we have discrete random variables. And it's basically the summation of all the possible values the probability mass function can take for all y that are less than or equal to x. Okay, so we don't, it's actually from minus infinity to x, this is the summation, but if x doesn't take any, the random variable x doesn't take any values like -5, -3, if it's first start taking values at 0, there's no reason for us to do the summation for all of them. They will be 0 actually. So start with the first non-zero entry in the probability mass function, and you will compute this. Cumulative distribution function is a non-decreasing function. Since probabilities are additive, since we are adding things, if you imagine how this fx is going to look like, it will start at 0 and go all the way to 1, sometimes staying constant. In certain intervals, it may stay constant, but it's a non-decreasing function, meaning that it will never drop to some level after it reaches that level. It will be a non-decreasing function, and it will take values. The largest value cumulative distribution function is going to take 1. It will put as the largest probability, and it will start 0 on the left-hand side. It will go to 1 on the right-hand side. And the set of all possible values of x is called the support of the distribution, f. So all the possible values x can take, there are random variables like 0, 1, 2, 3 in the case of the 3 coin tosses. That 0, 1, 2, those 0, 1, 2, 3, they are the support of the distribution of this f. Now, we are going to discuss continuous random variables later in chapter 4, but these two slides are like a heads up on how we will discuss them. I already mentioned these, so I'm going to repeat. This is repetition of what I already said in the previous hour. So point probabilities are going to be 0 because there are infinitely many possible outcomes in a continuous random variable. And instead, we will be using a probability density function, the same lowercase f, such that the areas under the curve are going to be used to compute probabilities. And in the case of continuous random variable, the cumulative distribution function is going to be described similarly to the discrete case. In terms of summation, you will have an integral, and we will integrate all the way from -8 to x, this probability density function. Basically, the probability density function is going to be the derivative of this cumulative distribution function. So the PDF actually is going to be defined as a derivative of this cumulative distribution function most of the time. All right, and we will discuss these in detail in chapter 4. So this was just two heads-up slides to what we are going to see in the upcoming chapters. Now, if you look at how the functions look like, the probability mass function and cumulative distribution function in the case of this 3 coin toss example, we see that the probability mass function is all 0. Since this is a discrete random variable which can take all 4 values, in all other cases, from all other places between -infinity and +infinity, the probability to obtain, for example, 0.5 heads is that probability is 0. Okay, so any real valued value of x is not possible since this is discrete. So we can actually indicate them as 0 probabilities on the probability mass function. And these points, 0, 1, 2, 3, will have non-zero probabilities on the probability mass function. If you look at our cumulative distribution function, the probability to obtain 0 or less heads, it was 1/8, right? So we start at 1/8 at exactly 0 here. This so probability of the cumulative distribution, in other words, let me write here, maybe let me annotate the capital F0 here. We know that is 1/8, right? The probability that we get 0 or less heads is 1/8. And therefore, as you can see, F0 is 1/8. But just tiny below this 0, for example, F minus 0.001. I mean, this is not a discrete variable, but if you look at this, any negative value here, the probability that to obtain a negative number of heads is 0, which is indicated here. So the probability, for example, to obtain 0.5 or less heads, if you just give another real valued number to this one. What does this mean? The probability to obtain 0.5 or less heads. It's also 1/8 because this will go all the way until we hit 1. As soon as we hit 1, basically we go here. Just consider a function that goes over this function from left to right, and whenever it sees something, it jumps to that point and it keeps adding the values here. So it's going to keep adding 0, 0, 0, 0 here because the probability to obtain exactly 0.5 heads or 0.6 heads to 0.7 heads is 0. So it's going to remain like this all the way until we hit the exact point 1, because at 1, 3/8 is going to be added to this one and we're going to jump here. So the cumulative distribution function seems like, it is like in discrete random variables, is not a continuous function that is integratable. Okay, so here it has jumps, these discrete jumps at these discrete values. This is what makes it a discrete random variable. Okay, just think about this 2 is not inclusive here because the probability of obtaining 2 or less heads is actually equal to 0.875, which is this point. All right, so when we come to 2, we need to jump here. That's why the ends of these are not included at the end of these line segments here. All right, now let me stop annotating and get back to the slides. Now, I'm going to show how the probability mass function looks like by actually performing a random experiment. If you perform a random experiment a large number of times, we will be able to figure out these probabilities like with the help of a simulation. we can actually compute these probabilities mathematically, the exact values. In many distributions, in certain cases, the exact values of the probabilities that x is equal to 0, x is equal to 1, 2, 3 can be computed. In the case of 3 coin tosses with equally likely outcomes, we already know that this is 1 over 8. This is 3 over 8, 3 over 8, 1 over 8. But this one in the book, this is the first time that a MATLAB code is given. And it will be a nice experience for you to try this out. You can go to Octave Online, octaveonline.net, and you will see that in this Octave Online, let's see, let me dismiss this thing. So here you can write, this is an interactive one. So you can, for example, I'm going to perform 10,000 experiments. So these are the number of experiments I'm going to perform. It's like I'm going to toss the coin 30,000 times. Each 3 of them will be one experiment. If we perform 10,000 experiments, let's generate random numbers. So this rand function generates a matrix of random numbers, 3 by n. So which means 3 by 10,000. It generated just 30,000 random numbers. Each 3 by 3, they indicate our experiment that we would perform. Now we can change. The good thing in MATLAB is that we can write equations that work on the entire matrices or entire vectors. For example, this u is less than 0.1 is going to work on the entire 30,000 numbers and going to, by the way, these random number generator, it generates a random number uniformly between 0 and 1. So some of these random numbers, for example, can we take a look at what u3 looks like? Or u31. I forgot to use this MATLAB. I don't know how the individual indices are, individual elements are indexed. I think it's going to be something like, is it something like this? No. Is it like this? No. Let me just check that. So how we access individual elements, or I can directly say display the entire U to my. So if I just write U, didn't display it, but yeah, let me just see. MATLAB individual matrix elements. So how do we do indexing? Okay, the United States. All right, so interestingly, we not use curly braces. Yeah, it's just, it says, so the square brackets are not used. It's like a function. So exactly, you're right. So for example, when you say U10, the 10th element, it's 091. So I think it's, what about, so the 10th element, I expected, since this is like a two-dimensional matrix, I expect it to be like it's going to show me 3 elements. But yeah, you may take a look at that later. But what you see here is that the numbers that it generated are between 0 and 1. So that's the important thing I want to show you here. The numbers it generated are between 0 and 1. Uniform, these are uniform random variables. But the coin toss event, whether heads or tails, is something binary. All right, so let me convert this by saying that y is equal to, so when you say y is equal to u less than, so how did we do that? Let me just look at the syntax. Yeah, I don't know why we need these parentheses, 0.5. So now when you look at y10, it's going to be 0. Okay, so it converts all the numbers less than 0.5 to 1. So the result of this comparison is either 1 or 0. So it basically discretizes the continuous random variables between 0 and 1. It discretizes them to zeros and ones. So here, 0 may indicate a head or a tail. In this case, for example, if you're interested in the number of heads, so it means that when it's a number between 0.3, 0.4, if it's between 0 and 0.5, you're going to treat it as a head. And if it's larger than 0.5, larger than or equal to 0.5, you're going to treat it as tails. Okay, so here when you say x is equal to the summation of the elements in y, what it does is it goes over all of those 10,000 elements. Okay, resume execution. Since I didn't put semicolon at the end, it's also displaying all the elements. So if you put a semicolon at the end, it's not displaying the results. So in order to show what u was actually, I should have just printed it like this. Okay, so this is what u is, 0.48. So these are, as you can see, the columns like this. With the semicolon at the end, it doesn't show me anything. It's just a statement like execute this one. But just writing it without the semicolon at the end, it says display this variable to me. So if we display x, what x is looked like, as you can see, it takes values. This is our random variable. It takes values between 0 and 0, 1, 2, 3. It's the summation of those. If you look at what y is just the 3 coin tosses. Every column here you see here is an experiment. I toss the coin 3 times, heads, heads, tails, heads, 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 tail, 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 heads, head, tail. So there are 10,000 of these. Okay, then simply writing this x is equal to sum y makes all these sums all these columns. Basically, this becomes a random variable. And in MATLAB, there's this histogram function. If you say histogram x, you'll get this figure which shows that out of these 10,000 values of x is an array which contains 10,000 different values for all of our 10,000 experiments. Out of those 10,000, roughly 1,200 of them, which corresponds to 1 over 8 of them, has the value 0, sum 0. So around 3,700. So this is again correspond roughly to 3 over 8 of them have the value 1. As you can see, they're not exactly equal. These two probabilities should be equal to each other, but since this is a simulation, we are doing something random. They're not exactly equal, but we expect these two probabilities to be equal to each other. All right, so we will solve more examples on MATLAB, and hopefully I'm going to remember the MATLAB codes that I had written earlier. Get used to writing code here on Octave Online. But this is basically showing the probability mass function for this experiment. Now, here is a different example. This is example 3.3 in the book. Errors in two modules which we are given that they are independent. Okay, so we are given two independent modules in a program. And the probability of errors in these two modules are independent from each other. So the probability to have, the random variable is defined as the number of errors we can have in a module. So as you can see, in module 1, we have 0 to 3 errors. It's possible to get 0, 1, 2, 3. If you add this column, you'll see that it adds up to 1. Okay, so this is like a probability mass function for the random variable, which tells how many errors you have in module 1. Let's call it x1, for example. x1 is the random variable that shows the number of errors, and that's the random variable number of errors in module 1. This is number of errors in module 2. As you can see, the number of errors, 3 errors in module 2 is impossible. It's probability 0. But if you add up these probabilities, you see they also add up to 1. So these are probability mass functions. If we're given that these two modules are independent from each other, the occurrence of these errors in two different modules are independent, Then these two events, for example, the event, what is the probability that, so I'm getting a new one, let me erase the other ones. Discord, yeah. So for example, the probability that x1 is equal to 2 and x2 is equal to 1 could be computed by multiplying these probabilities, multiplied by probability of x2 is equal to 1. Okay, because these are, when I say these events are independent, then I can just multiply the individual probabilities to get these. In other words, this in the probability mass function, this is f, if I multiply f2 with f1 in my table, it will tell me the probability of this event. All right, so here, if y is the total number of errors, what is the probability mass function and cumulative distribution function of y? So this is something interesting. We define a new variable. Let's let y be equal to x1 plus x2. Now this is a new variable. What is the probability mass function of y? First, we need to figure out what possible values y could take. And we'll see that it can take values from 0 to all the way 1, 2, 3, 4, 5. Can it take 6? No, because module 1 can have at most 3 errors. Let's get back to this. Module 1 can have at most 3 errors. Module 2 can have at most 2 errors. So y can have the largest value y can take is 5. If you write 6 here in your table, this f6, you should write it as 0. So how do we compute the probability of f0 in our case? What is the probability of y to become 0? The only possible way to obtain 0 with these individual random variables is both becoming 0, right? So what is the probability of x1 is equal to 0 and x2 is equal to 0? This we can simply multiply these two given probabilities, 0.5 and 0.7. So in other words, this is going to be 0.35, which I obtained by multiplying the individual probabilities of being 0 in both cases. What about f1? How would you compute f1? What is the probability that f1 is, the y is equal to 1? There will be two cases just like that, different outcomes. Different outcomes here will give me the value of 1. For example, x could be 1, x could be 0, x2 could be 1, or x1 could be 1 and x2 could be 0. And these events, as you can see, this and, for example, 1 and 0, and 0 and 1 are two mutually exclusive events, so they could be added. So in order to compute f1, all I need to do is multiply 0.3 with 0.7, which indicates the case where module 1 has 1 error and module 2 has 0 errors. That's that event. But there's the other case, y could obtain the value of 1, where the second module has 1 error and the first module has 2 errors, 0 errors. So it's 0.21 plus 0.10, it's going to be 0.31. Okay, so now I obtained this 0.31 by multiplying 0.5 with 0.2, which indicates 0 error in the first case, 1 error in the second module, plus 0.3 times 0.7, which is 1 error in the first module, 0 error in the second module. So you need to, 2 could be obtained in 3 different ways, right? It could be 1, 1, or 2, 0, or 0, 2. This is all the cases where you can obtain it too. And so like this, you're going to find those individual probabilities and find the probability mass function of y. By adding up those individual probabilities you obtained for y, you can obtain the cumulative distribution function. Okay, so this example, let me just show you in the book how this example looks like. Let's go to chapter 3, and right here, let me weave it. Where is the total number of variables here? We have seen this one. Yeah, this one. Example 3.3. Errors in independent modules. So the fact that they're independent from each other is given in the name of the question. There's no statement actually that indicates they're independent here, but the name of the example tells us they're independent. So here, as you can see, 0.31 is found like this. 0.42, we have 3 cases. We need to add up these 3 cases. And after we find all these probabilities, we can check that it's actually indeed a probability mass function by adding up all the values we have computed here. And if they all add up to 1, it means that we didn't, I mean, that's one of the checks that are needed. It doesn't always mean that we have did everything correct, but if it was something other than 1, we would be sure that we made a mistake. And the cumulative distribution function just adds up these values. 0.35, then we add to that 0.31, we add to that 0.18. As you can see, it's a non-decreasing function. Okay, we talked about types of random variables. Now we can talk about distribution of a random vector. The interesting thing and the analysis of these probabilities are, did I just close? That's here actually. The analysis of multiple random variables at the same time, which we call random vectors. So a vector of a set of random variables, a sequence of random variables, is called a random vector. And the study of all these together simultaneously, like we had x1 and x2, right? In the example, the modules and the errors in module 1, the errors in module 2, they are 2 different random variables, and when we analyze them together, they become a random vector. When we analyze everything together, and this is what we usually do in machine learning, we study several random variables simultaneously because we usually make multiple measurements, multiple observations in different settings. For example, what is the probability that a student is going to get a job in Google, for example? You actually you have to measure different features for this student. What is the cumulative GPA? What is the grade he got from the algorithms class? What is the likelihood he will do applications abroad or job applications abroad? These things, or these things, or whether he's actually participate in a social club in ODTÜ. That's a feature. So all these features that you collect for a student are different random variables. And with that, for example, you're analyzing another random variable to get a position abroad in Google or some other company. That's a feature that's the random variable that you want to study. And basically what I'm saying is that we measure multiple factors for certain objects, and this leads to the study of several random variables at the same time. And so this is called a random vector. We have 2 or more random variables. The distribution, when we study the distribution of this random vectors simultaneously, it's called the joint distribution of x and y. And most of the cases, when you have multiple features, especially more than 2, the joint distribution is very difficult to obtain. You have to have lots of data points that shows this, that, and that. All just consider combinations of all possible features, and think of these features as dimensions in a Cartesian space. Each additional feature increases the dimension 1 more, and it increases the available points that you're going to put in this space exponentially. So in order to have a joint distribution, you have to have enough number of examples that fill in this space. Most of the cases, this is not possible. For example, with just 1 million samples, it's impossible to fill in a joint distribution feature space of 20 features if each of them take binary values. Imagine you have 20 binary features. They just take 0 or 1 values. Whether you did this or not, you did this or not. So you ask 20 different questions to an object. Does this exist or not type of questions. 20 of them makes, if you look at the joint probability distribution, the number of outcomes that you can have is 2 to the 20. The sample space is this much. So 2 to the 20 is a large number. And if you with just 1,000 observations, for example, there will be exactly. And also the 2 to the n, these are the any individual outcome will be one of those 2 to the n. And having different we will be able to have a lot of different events we will be able to measure, but just picking a particular individual will be a point in that 2 to the 20 outcome space. Exactly. Every new variable, we have 2 to the new power. So every new variable adds a new dimension. So you just multiply it by 2. Okay. So imagine you have a certain for example, you measure something like the age of a student, and then you add a new feature, hair color, black or brown. It immediately multiplies all the possible data sets you have by 2. There are so this is therefore each feature increases your dimensions exponentially, and try to have samples in that feature space so that we can guess these probabilities is really difficult. So usually the joint distribution is not used, but the thing is that with the help of conditional probabilities, we can compute the joint distributions, and conditional probabilities are easier. It's like you just fix some of the dimensions, then you take measurement in the other dimension. So it's like fixing one dimension and looking at the other reduces the dimensionality, again, exponential, logarithmically, dividing by 2. So these joint probability distributions are computed with the help of conditional probability distributions. But if somebody gives us this joint distribution, it contains everything, all the information about unconditional distributions, individual distributions of the individual variables can be computed from there, which are called marginal distributions. I'm just going to show you an example in the last 10 minutes. For example, let's look at this one. We are given, so let's ignore this last part. Let's ignore the entries that are here. Okay, let's ignore these parts. These 8 numbers that are given to us, they comprise the joint probability distribution of x and y. This is the variable x, which gets one of the 2 values 0 and 1. This is the random variable y, which gets one of the 4 values 0, 1, 2, 3. So the joint probability distribution is a table of n by m, where n is the number of values x can take, and m is the number of values y can take. Okay, so it will be a table like this. And every individual entity here in this joint probability distribution table, the probability mass function that is given to us in this discrete, both of them are discrete variables, tells us what is the probability that x is equal to this, for example here, x is equal to 0 and y is equal to 0. Okay, so we are given these intersections. What is the probability that x is equal to 0 and y is equal to 0? What is the probability that x is equal to 0 and y is equal to 1? So these individual probabilities, all of them, the joint probability, they should entirely, in order to make it a joint probability, joint dense distribution, they need to add up to 1. We can check that whether that's a valid joint probability distribution. These 3 make 0.6, 7, 8, 9, and these 2, they add up to 1. Now, in order to figure out what is the individual probability of x is equal to 0, which is not given in this table, right? X is equal to 0 is not given in this table. But we can find, we know the law of total probability, right? X is equal to 1 simply is the addition of all these. Y is equal to 1, y is equal to 0, y is equal to 1, y is equal to 2, and y is equal to 3 are mutually exclusive and exhaustive events. These are all the possible values y can take. Therefore, if I add these intersections, this one added 0.2, 0.4, 0.45, 0.50. So this 0.5 here, which I erased actually, this is a row sum of this. It's basically gives me the individual probability mass function for x. 0.5 is the probability that x is equal to 0. Oops, immediately I clicked something outside the PDF and the annotate just disappeared anyway. So if this is 0.5, since it can take only two values, the other is also going to be 0.52. We can do the same thing for computing the individual probabilities for y. For example, x can only take values 0 and 1. So these two events are mutually exclusive and they're exhaustive. So in order to find the probability that y is equal to 0, I can just look at what is the probability of y is equal to 0 and x is equal to 0. Y is equal to 0 and x is equal to 1. If I add up these two probabilities, it will tell me what is the probability that y is equal to 0. Okay, which is 0.40. Again, these column sums will give me the individual probabilities. Now, let me ask you a question. If I was given the individual probabilities, if somebody gives you just these, px and py, is it, instead of, because px and py, the total number of values that you're going to give me is going to be n plus m, right? Px contains n values, py contains m different values. Instead of giving me the entire n by m table, why don't you give me just px and py? Then I can compute the joint probability distributions from these individual distributions. Is it possible? For example, which information do we lose here? For example, why is it necessary to give these entire 8 table? I could have obtained, or let me ask you this way. Is it possible to obtain exactly? This is the answer. So actually, Berk, thank you for the answer. They may not be independent. If they're independent, we can multiply these probabilities to find these joint probability distributions. So px is equal to something and py is equal to something will be a multiplication of these two individual probabilities only if x and y are independent. If they're not independent, for example, 0.5, 0.4, you multiply these together, you get 0.2. Nice. It seems like they're independent, but you have to do this check for all of them. For example, look at this one, 0.5 and 0.3. If you multiply these two, what do you get? 0.15. But what do you have here? 0.20. What does this tell us? These events, x and y, are not, these two random variables are not independent from each other. Okay, when they're not independent, as you can see, that's exactly information loss we have here. If somebody gives us this m plus 1 items only, we would be able to compute joint probability distribution only if all of the events are independent. If there is some dependency between those events, they like causality relationship, for example, if I mentioned this, getting a position abroad, for example, I talked the cumulative GPA and getting a good grade in algorithms class, for example. These two probably are related, right? If you look at somebody who has a high GPA, they probably should also get a high grade in algorithms class. You cannot say these two are independent. So probably there will be correlation between those two. And in that case, we will not be able to directly multiply individual probabilities to get the joint probabilities. All right, so that's one thing. Only for independent random variables we can. If you're given that they're independent, like the example of this two independent modules, we were actually given a table which was not 4 by 4. You would have to be given 16 different values, a 4 by 4 value table, in order to find the individual probabilities. But we were given just 4 plus 4, 8 values, because we were told that they're independent. If we know that they're independent, we can fill in those 16 values by just multiplying each one of them individually. Multiply this with this, this with this with that. So all these Cartesian product multiplication, we'll be able to find the joint distribution given that they're independent. Let me ask some questions to you. For example, this one, we know that we have seen by this. Is there any example on this table, any other entry? But with just this entry, we have seen that these two, with a single entry, is sufficient to find that they're not independent. And by looking at this, for example, by just looking at one entry, I did not just jump to the fact that, 0.4, 0.5, they are independent. It makes 0.2, they should be independent. I didn't say that. But now, can you tell me, is there any other entry in this table besides this one that tells me that they're not independent? Any answers? Well, what you should do right now is try to multiply something here with something here, and to see the result is not the same as something here. Yeah, every other one's, row 0, column 2. For example, this one is also not true. This one, all the other ones, if you multiply them, you don't get the result. All right, so this is what the joint probability distribution is. The entry in the probability mass function, joint probability mass function, tells us both of the events, the intersection of these two events, where x is equal to x and y is equal to y. So for all possible and different pairs of y, this tells us, and these are all mutually exclusive and exhaustive events. So every entry on this table here, you see, there are 8 mutually exclusive and exhaustive events. X is equal to 0 and y is equal to 0. That's mutually exclusive, and all of these together, they are exhaustive, but it's mutually exclusive of 0 and 1, 0 and 2, 0 and 3. Okay, so we can add these. That's why we can add them, the probabilities directly, because they are mutually exclusive of each other. All right, so I talked about the marginal probabilities. We can just add up. This is the same as the law of total probability. You can just add up all the probabilities that y can take to figure out the individual probability that x is equal to x. We just did that on this table as an example. And this was the question that I asked you, whether it's possible to have whether it's possible to get the joint probability distribution from individual distribution. And this is only possible when we have independent random variables. Okay, we talked over this example. I think it's a good way to stop now. On Tuesday, I'm going to talk about expected value, variance, and some students cannot see the chat. Some messages may be sent privately. That's actually, maybe you may not. I don't know why sometimes Cisco WebEx disallows students, does not permit students to send chat messages to everyone. Maybe it's some setting that I might need to change. So most of the chat messages that you're sending and you're seeing, you should be seeing on my screen, or maybe the screen share does not show you the chat. So the messages you sent on the chat are sent privately to me. So you may not be seeing, there is no send to everyone. So I'm going to check the settings for Cisco WebEx next time so that everybody is able to send chat messages to everyone. So right now you can only send chat messages to me privately. So I will make sure that it's going to be corrected. So you'll be able to send chat messages to everyone in the lectures, upcoming lectures. All right, so on Tuesday, I'm going to continue with expected value, variance, and standard deviation, and we'll start talking about specific discrete variables, family of discrete distributions. All right, thank you, everyone. I will stop recording now.